In this series of videos I'm attempting to repair and restore this PDP11-34A vintage computer. In the previous video in this series we found a problem with the scratch pad memory that came to light after I'd carried out some early repairs. And what's happening is if we try to access the scratch pad memories, which is just a set of internal registers used by the CPU for its general purpose, plus some very specific purposes such as stack pointer, program counter, that sort of thing. But when the system's not running, they are just really very similar to an SRAM, and we can't write to all the bits, so it's 16-bit SRAM in effect. But if we try and write to one of these addresses, so the first one is the R0 register, and if we load the address of that, which is 777700, and we try and write a value to it, so if I try writing all ones to that address, that's all ones in a 16-bit system, and if we try and deposit that, what happens if we try now to read the same address, notice that it hasn't written all the bits. It's actually written just the lower 8 bits, and the top 8 bits have remained at 0. And that's true through the rest of the registers. So if we try and do the same thing with the other, they're called scratch pad, but as I said, some of them are specific registers. But if we try and write a specific value to these, then it doesn't work. So we'll start with the first one, and we'll try and write ones to all 16 bits in all of them. So I've written a 1 to all the bits in all the scratch pad memory registers, and you'll see that we ran off the end again. And if I now reload the address of the first register, that's R0, and we try and read this, so again we've only written the bottom 8 bits. And the same is true of all of them. If you look at the bottom 3 digits here, hopefully you can see this, they're all saying 377, which is all ones for 8 bits in octal. So if we look at the rest of the registers, the bottom 8 bits have been updated correctly, but the top 8 bits have not. So we'll do the same thing now, but writing zeros to the registers. Okay, so I've written zeros to all the registers. We'll go back to the first one, and we'll try to examine it. And again, if you notice, the bottom 3 digits have been set to 0, apart from, because these are active registers, you'll find that some of them will change when you do certain things, so don't be confused by that. Okay, so it appears it's just the top 8 bits that we can't effectively write to. It seems we can read them, or at least we're reading something. Now this could be multiplexers, it could be the memory itself, it could be the control lines. So what we're going to do to start with is have a look at the memory chips. So there are 4 sections in this. The CPU slices the data path into 4 4-bit slices. This is the memory device we're talking about, and of course there are 4 of them. The circuits are very similar. It's just really the way this works is you've got the ALU, and there are just multiplexers that determine what the data is that is going into the ALU and what the data is that's going out onto the data bus. But this is what we're interested in. The ALU can select any of the scratch pad registers to use as a source for data, and that's what comes out. So what we're going to monitor here, and I've got the logic analyzer set up to do this, is the 4 data input lines, the 4 data output lines, the 4 address lines, and the 4 control lines. And that will allow us to see if data is making it to the memory, and if data is making it out of the memory, or if there's a control line or addressing issue. So as I say, I've got the logic analyzer set up, so I'll move the camera. So what I'm going to be doing here is trying to write values to the various scratch pad registers, starting at R0, working our way up. And because we're looking at 4-bit slices, and I've identified the 4 devices that we are going to be using. Sorry if this is flapping about as a fan blowing onto it, but the devices are E8, E29, E19 and E39. They're the 4 scratch pad rounds. So for the lower 4 bits, the hex value for 4 ones, and then that's the number, and at the top we have the octal representation for the same number. In this case it's 17 octal. For the second 4 bits, second device, the lower 4 bits don't matter, but the second lot of 4 bits need to be all ones, so I've decided to use ones for the don't care bits, and that results in an octal number of 377. And then for the third device, similar sort of logic, we end up with an octal value of 7777, and if we need to we'll move on to the fourth. So I've got the logic analyzer connected, and I'll move you so you can see the logic analyzer, and we'll try running this test. So I've got the analyzer set to timing mode this time because we won't have access to a CPU clock to clock the analyzer, so I need to run it in timing mode. I've got the 4 address lines connected, the 4 data in and the 4 data out, as well as the 4 control lines, and so we can capture the behavior of the individual scratch pad memory devices. So we're looking at the first one. This is E8. I'm going to arm the analyzer, and I'm going to try and write a value of 0 to that particular register. So as you can see, the analyzer was triggered, the address was 0 as it should be, the data in was 0 as it should be, data out was 0, the high going clock pulse, and we have the output select and write enable goes low to enable the write. So this time I'm going to try and read the device, so we'll rearm the analyzer. Notice we have exactly the same thing. The only difference is the write enable line stays high because we're reading it, we're not trying to write it. And what we'll do now is try and write all ones to that particular address, which, if you recall, is a value of 17 octal. And indeed we have succeeded. We've got the address at 0, and we've got 17 going in, 17 coming out, and we can see the write enable was strobed to write the value into memory. What I'm going to do now is rearm the analyzer and just press deposit again, and we should now see the same thing, but the address should increment to a 1, and it has done. So we've done the same thing to the R1 register, and we can now work our way through the registers and check that the entire scratch pad memory device works. I'm going to shortcut this. I'm going to assume that the rest work. Generally speaking, if it works this far, that it'll work throughout, but I will test the entire set of registers off camera. What I'm going to do now is move the clip from the E8 device to E29, which is the second group of 4 bits. We'll now clip to the second device. We'll rearm the analyzer, and this time I'm going to try and write a value of 377 because we're looking at the second group of 4 bits. So we should be writing 17 as we did here, but into the second device. It'll look very similar if it's working. The only thing to remember is we're kind of offset now by 4 bits. So I'm going to try, first of all, writing a 0. So we're armed, and that's worked fine. You can see we've got 0 in, 0 out, address of 0, the clock, and the write enable and output to select, and that's all looking fine. I'm going to try and read the same address, rearm the analyzer, and examine, and again exactly the same thing, but the write enable is staying high because we're reading it and not writing, so that's fine. I'm going to rearm it, and this time I'm going to send the 377 value and see if the bits are all set to a 1. So I'm going to deposit that, and that's looking good. So we've got same 17, like I said, we're offset by 4 bits, so this is just the upper 4 bits of that 377 value. But they are looking good. What I'm going to do now is try and read this, and it should read back as 17. And again, looking good. We're getting data out 17, and so that memory device is working. It's stored the values that we put in. I'm going to move the test clip now to E19, and that's the third group of 4 bits. I am now clipped onto E19, which is the third device. We're going to rearm the analyzer, and I'm going to try and read that device. So again, we'll still be looking at a range of data from 0 to 17 octal, but we are now offset by 8 bits. So I'll enter the address of R0. I'm going to try and examine that address. So the bits are all set to a 1. So it could be that that's just the value they had when they were when the machine was started up. I'm going to rearm and try to write zeros to that device. Okay, so the interesting thing here is we've got an address of 0, which is correct. The data in is 0, which is correct. So the data that I try to send is getting here, and but the output's staying at 17. The output select is changing, but the write enable is not changing, so we're not getting a write enable pulse. I'm just going to try depositing the 0 to the next address and see if the address is correct. It should increment and go up to 1, which it has done. The data out has changed, but this is a different register now. So it looks like it's just putting out the value that's already in the register, it's not updating it. But that's because the write enable line is not strobing low. It should go low as it did before when we try and write data into that device. So we'll just move the camera and then try and figure out what's going on with this. So if we look at the schematic for this, this is the first device we looked at that was working fine, so there's no problems with that. Notice these gates up here. There are exceptions to when you want to read and write certain blocks of data. So it actually handles the bottom 8 bits separately from the top 8 bits, but normally for a 16-bit write it should enable both of these. Now on these diagrams, when you see a little branch like this on a connection, it means it goes somewhere else. And you probably can't read it, but this says output store low, and if we look at the second page, the control line this time, you don't have the gate, but it says output store low. So that one line controls both of these devices, and both of these we know work. If we go on to the next device that we know was receiving the data, but the write enable was not strobing, what's interesting is we have this control gate, and this is used to inhibit writing to this device. But again, notice this little branch, this spur we've got sticking out, and that's labelled write high low. And if we look at the next sheet, which is the fourth device, or the top 4 bits, notice on the write enable line we have write high low. So in other words, these 2 upper memory chips are controlled through a common line, and that is controlled through this single gate. So what I'm going to do is check what's going on with this gate during a write cycle, and we'll see if we're getting any activity. So the first thing I want to do is look at pin 13. So this is an OR gate, and this line is used to effectively disable the write. So if it goes high, then it will disable the write pulse. So the first thing I'm going to do is look at pin 13 on this device. You won't be able to see the device, but you'll be able to see on the scope the level on that pin, and it's the yellow trace that you're looking at. So I'm just going to check that line, and that is low. So I'm going to monitor that with the scope while I try to write to it. So I'm now going to try and deposit something. Okay, so that's stayed low, which is good. It means it's not getting a momentary pulse to disable anything. We'll now look at pin 12, which is the write strobe pulse. So this should be strobing whenever we try to write to the two upper memory chips. Okay, so that's high. That should strobe low when I try and write to this memory, so I'm going to try and write to it now. And I don't know if you noticed that, but it did indeed strobe low, so I'll do that again. So as you can see, we're getting a pulse there, so that's strobing. And so finally we'll check the output of this gate. That's pin 11, and that's what controls the actual write enable for the two upper nibble devices. So it's pin 11. Okay, already that's not looking right. It's stuck halfway. It looks like the output on that particular device might be faulty, or there could be a problem with one of the two RAM chips. I'll try and write anyway, and we'll see if we get anything on there at all. So I'm going to try and write now. Okay, so nothing whatsoever. We'll try one more time. So nothing. So it looks like that particular device has failed, that particular gate. And if this gate fails because it controls both of the upper memory chips, it effectively stops us writing to the upper bits. So I'll try replacing this device, and we'll see if that restores operation of our scratch pad memory. So I've replaced that device, and we'll give it a quick test. And indeed it shows up as being faulty, so no surprise there. What we'll do now is we'll move the camera back so you can see the analyzer screen, and we'll try and rerun the same test and see if it looks any better. I'm clipped back onto E19, which is the device that wasn't showing the correct data before, and we'll try writing to the R0 register on the analyzer. So I'll try depositing the value 7777, and that should set all the bits in that device to a 1. And this time it's looking much better. You can see that we've got address 0, which is the R0 register, data in is 17, but this time the data out is 17, and the write enable is actually strobing, which it wasn't before. We should now be able to set this back to a 0, so we'll rearm the analyzer, and I'll try depositing a 0. And again it's written a 0 through. So I won't bother testing the upper device just now. I will do that off camera, and I'll fully test all these, but just to get this video moving along, we'll look back down at the device and see if we can actually get it any further through its boot process. So we can now successfully read and write the various registers. So if we go back to the register R0 that we couldn't read and write properly before, and try writing a value of all 1s to that, and then we'll try to read that back. Notice it's now all set as 1s. If we try to write a 0 value to it and examine that, again it's reading back as 0. So we can now properly access the scratch pad memory. And on top of that, the memory management, I did just check off camera with the scope, and the memory management does seem to be behaving itself. At least it's not sort of poking its nose in where it doesn't belong, which is, it kind of fooled us into thinking that the machine was running better than it was, and it just coincidentally pushed a few memory banks into operation when in reality they weren't really accessible. So what I'm going to try and do now is actually boot this from the, we've got the bootloader card, and we'll see. I won't try booting it to floppy disk, I'm just trying to boot to the console emulator, and we'll see if it actually stays running. So let's give this a go. Okay, well it still says it's running. Okay, and I'll bring the console up in the corner of the screen, and you can see it has actually booted. So we'll try restarting and see if that repeats. Okay, so that's a huge step forward. What I'm going to do now, just as the final test in this video, is I'm going to try entering the test program that we've been using and see if that will actually run. So if you recall, quite a while back we had this test program, so I'm just going to enter this and we'll see if it's capable of outputting data to the console. Okay, I've entered the program. We'll go to the start address and we'll try and run it and see what happens. As you can see, the CPU is now back up and running, but I think it's running far better than it originally was. I don't think it was running properly previously. It would only work at certain addresses, whereas now what I'm going to try and do, I'll do it off camera, I'm going to try and enter this program into different memory addresses. Now I had tried using some of the tools that are available for doing the memory test, but unfortunately with this sort of fault, because the banking was kind of messed up and it was just repeating the same test in the same banks, the memory diagnostic didn't pick up the fact that it was not writing and reading from the bank it thought it was. So what I'm going to do now is I'll load different programs into every single available bank and make sure that the different programs are actually in those banks. But it's a big step forward. We've finally got the CPU back up and it can now run programs from RAM, or at least it apparently can, and hopefully it's a bit more stable than it was previously. If all these tests are fine, I'll say I'll do it off camera, it's a lot of testing, be 3 or 4 hours of testing, and if all the tests are fine, then in the next video we'll go back to where we were quite a long time ago, hook up the floppy drive and try booting from it and see if we can get any further. This time I suspect it might get a bit further. I think it was failing before because the system just wasn't able to properly access RAM. It just seemed like it was, but hopefully now we'll get a lot further.